Hello, in this video I'm going to go through the difference between centre of mass and centre of gravity because I hear a lot of people getting confused about these and just treating them as if they're exactly the same thing. And the names in themselves tell us that they're not, because we've got one of them centre of mass, which is to do with matter. That's one of our fundamental topics of physics. And then we've got centre of gravity, which is to do with force, another one of our fundamental topics of physics. So if we're saying these things are the same, which obviously they're not, then that's suggesting that we don't know the difference between matter and force, which is not a good look. So let's start with centre of mass. Say we've got, this could be any object really. You might have a surface, you might have a volume. So say this was a cube. Then the centre of mass is only concerned with the object itself and how the matter is distributed within it. And then we're saying, well, if we were going to reduce all of that matter down to a single point that was at the center of that object, the middle of where the matter distribution is, then where would we put it? Now, for a uniform distribution of matter, this is quite straightforward. From a theoretical point of view, you just find the lines of symmetry and where the lines of symmetry intersect. We've got three of them here for this cube. That's going to be our center of matter. For odd shaped objects, irregular objects, or ones that have got a non-uniform matter distribution, it can be a lot more difficult. Say with this cube we had more of the matter on the left hand side than the right hand side. That's going to shift the center of mass off to the left towards where most of the matter is. So it's not always that easy to just say, okay, well, here is the center of mass of an object. But there is another trick that we've got with this, which is one of the key properties of center of mass that we can start looking at experimentally. That if we apply a force where the line of the force goes through the center of mass of an object, then that object won't rotate. It will just translate linearly through space. It won't rotate while it's moving. So this is something that we can look for. You can even trial it out with things. You sit something on a table, and particularly if there isn't much friction on the table, or you've got some object that moves around quite easily, so we're minimizing any kind of stabilizing force. You get an idea of where you might want to push on the object in order to make it move without rotating. So if you can do that, then you're getting close to where the center of mass is. That's what's going on with center of mass. It's just the property of the object and the matter distribution. Center of gravity is different, although, as I said earlier, it can coincide in location with the center of mass. But with center of gravity, we're thinking, well, where could we reduce the force of gravity down to that's been exerted on a particular object? Now, if we've got a uniform object, say this was just a surface, save me drawing out a volume, and we got a uniform gravitational field. So we draw in all of our gravitational field lines, and these are all evenly spaced, and they'll be going through the object. I'll draw them all the way across. So we've got a uniform gravitational field going on here. Every part of this surface here is going to experience exactly the same force due to gravity, and the center of mass of the object will be in exactly the same location as the center of gravity. Even if the center of mass was off center, if this was a non-uniform mass distribution and we had the center of mass up here, say, for this surface, well, the force due to gravity, because it's proportional to the mass, that's just going to shift into exactly the same location. So while we've got a uniform gravitational field, center of mass and center of gravity are going to coincide with each other because of this proportionality between the force and the mass. The difference comes in when we start getting a non-uniform field. So say, we spend a lot of time looking at force due to gravity on the Earth, because of course that's the one that we're experiencing all the time. And we approximate the Earth's gravitational field, at least in an everyday setting, to being uniform, because we're not getting that far away from the surface of the Earth compared to the radius of the Earth, which is considerable. What if we've now got a case where we've got some epic skyscraper, and these things are getting bigger and bigger? where, okay, let's have a simple case of this is a uniform mass distribution in the skyscraper. So the center of mass of the skyscraper is right in the center along these lines of symmetry. So it's at the geometric center of the shape. Now, if this is high enough, we're getting these field lines spacing out. So the force due to gravity at the top of the skyscraper is less than the force due to gravity at the bottom. This is going to have the effect of shifting the center of gravity down, because there's more gravity being felt at the bottom than there is at the top. So it's going to move the center of gravity down compared to the center of mass. We've now got a difference between the location of the center of mass and the center of gravity because we've got a non-uniform gravitational field. So that's when you can start getting differences between where they're located, because one of them is just the distribution of matter, the other one is the distribution of force experienced by that matter. So this is where it's bringing in, you know, we said before, it's just for this uniform gravitational field. We're just looking at the proportional to m part of it. Once we get into a non-uniform field, we're now looking at proportional to m over r squared. So we're bringing this r squared in, which we don't care about in a uniform field. If it's a uniform field, we're not doing our gmm over r squared. The r squared isn't doing anything. It's not dropping off. It's not a radial field if it's one of these uniform ones. We're in a radial field. We've now got inversely proportional to r squared as well as proportional to m. And that's where you're going to get a difference between center of mass and center of gravity in their location. So it's important to be aware of these things. And really, if you've got someone sitting there saying, oh, I don't know the difference between center of mass and center of gravity, then they're just on the same misunderstanding really as people have when they say, oh, I don't know the difference between mass and weight. It's exactly the same thing. We're looking at the difference between matter and force in both of these. So make sure you're clear on this, otherwise you're not getting to grips with these fundamental properties of physics, these fundamental topics that we're looking at.